today we have Stefan from the GI Research Group. He recently submitted his thesis and he's going to talk more about it. And he started his work in EGG from his master's onwards, and he's carried that on to a PhD, and we'll learn a bit more about the fact, fiction, and clinical relevance of EGG today.
Hi everyone, welcome. Glad to see so many faces here. Well, it might just be the GI group. I'm glad to see a big diverse group from the entire ABI. So I'm here to talk today about my topic, an electrifying journey into electrogastrography, EGG, fact, fiction, and clinical relevance. Now I wish that was the title of my PhD. It wasn't. We've kind of jazzed it up for you today. The actual title was an experimental and theoretical analysis of the electrogastrogram, EGG. So my supervisors were Dr. Ping Du and Professor Liu Cheng, and I've been working on this for 4 years here at the ABI. So before I jump into kind of the work that I did and the kind of the specialty that we've been working on, I'm going to go into the background of the anatomy and physiology of the stomach, and then I'll work my way forwards and go from there. So the stomach is an important part of the digestive function, GI tract, and plays a vital role in digestive function. The stomach is controlled by electrical propagations, and this electrical propagation is controlled by the ICC in the stomach. These ICC cause depolarizations at different speeds, radially and longitudinally, and we see these propagations going down the stomach, and they're called gastric slow waves. Normally, this propagation occurs at about 3 cycles per minute. And so we've got a quick little demo here of what that actually looks like if we're going to look at it endoscopically, with an endoscopy, or if we're going to look at it serosally. So if we look internally, we can see these slow moving waves going down the stomach at about 3 cycles per minute. This is to help break down food and push food from the stomach into the lower GI tract. Now, if we actually look at this serosally on the stomach surface, we get waves that look like this. So here we can see those 3 waves per minute, rapidly depolarizing circumferentially, and then moving longitudinally down the stomach, which is functionally pushing that food down into the lower GI tract. So why do we care about the GI tract, and why do we care about stomach dysmotility and GI disease? So the cases of GI reporting or GI dysfunction globally is on the rise, and we see an increase in prevalence and reporting of this globally. This places a large burden on clinicians, with an estimated 32 million physician offices visits per year and 8.6 million emergency department visits per year. This is just in the US, and it is reported by the CDC. This has an annual cost of approximately $142 billion a year. Now, I will pause myself there. What we're trying to do with my research is not trying to tackle that 142 billion. That includes things such as cancer, lower bowel, and a whole range of anything related to the GI. So that number is inflated, but I wanted to show that number just to kind of express to you that this is a real problem with a large financial burden on the system. People with GI motility disorders currently have very few clinical diagnosis options. And with those diagnostic options available, they're often misdiagnosed and leave the patients really with a sense of dissatisfaction and misunderstanding of what they really have going on in their bodies. I can't reiterate to you guys enough that if you have this kind of disorder and you're going to the GPs and they're telling you that there's nothing wrong, how disconnected you feel from the medical system, because if they don't know what's wrong, they can't provide any clear future for treatment options, and going ahead, you have to live with these kinds of diseases. And so I guess this is kind of where my PhD works to try and come into. So we're trying to develop new clinical methods to diagnose gastrointestinal disorders. So most people will not have heard of electrogastrography, EGG, but you will have heard of the electrocardiogram, ECG, or the EEG for the brain. So the EGG uses the same fundamental principles as the ECG, whereby we gain an understanding of the electrical propagation of the stomach by placing electrodes on the body's surface. This gives us clinical information such as, this gives us information about the slow waves in terms of rhythmicity, frequency, amplitude, and propagation. But unlike the ECG, which is considered one of the most widely used clinical tools in the world, EGG is unheard of. It's not really used anywhere, and is mainly primarily used as a clinician's tool. And this is due to a number of limitations that we see in the EGG. So before I jump into those limitations, I'm just going to show you roughly how we actually analyze EGG. So if we look at the top image here, we can actually see gastric slow waves recorded from the serosal of the stomach. And we see nice sharp deflections, approximately every 20 seconds, which is so we can know that there is actually slow wave activity. We can take EGG recordings, shown in the bottom image here, and we see that the amplitude of that EGG recording is only 1/10 the size of the actual serosal activity. But in terms of the frequency, you can see that the rhythmicity is the same. So what people have been doing in the past is they've been doing a spectral analysis on this, or a Fourier transform, and been saying that it's been going 3 cycles per minute over the entire recording period. And that's really where the test finishes. They say, did you have 3 cycles per minute activity? Were you within that range of normal activity? And if not, you were abnormal. But that's kind of all the information that they've actually been able to give you. And so this has led to a number of limitations in the clinical reporting of this. And so they haven't actually been able to give clinicians any diagnostic information, which is why it hasn't been widely adopted globally. So some of the big limitations of the EGG is the lack of standardized techniques. This includes electrode placement, test meals, recording periods, signal processing, and the normative range that we define as normal. So what we've got here is an example of 4 standard EGG methodologies. The red indicates recording electrode, the red dots indicate recording electrodes, the green is the ground, and the blue is the reference. And so even in the EGG field, we don't have a standardized technique. Everyone's got their own technique, their own practices. They're all doing their own thing because they think that they know what is best for the EGG and giving the clinicians the best outcomes. Because of that, we can't actually form a normative database. We can't go between clinics to clinics and actually give ourselves a large database to accurately diagnose patients. And so this has led to the low discriminatory power to differentiate between healthy controls and normal patients, where really we can't diagnose these conditions. Part of that issue is because of the incomplete description of the actual serosal activity and the body surface. Right now, our understanding finishes at there's 3 cycles per minute. That really doesn't tell the whole picture. We know from serosal recordings that the propagation direction, the velocity, the number of simultaneous waves, all give us indications of what's happening on the stomach. And so a simple 3 CPM won't cut it. And so today I'm going to talk to you about my PhD and how we try to address some of these limitations and revitalize the EGG into a more clinically relevant device. And so my PhD was kind of working in a circular fashion. We developed gastric simulations, which we'd then use to define new methods to analyze the EGG, and then we'd aim to experimentally validate. And we'd just go round and round and round, trying to redevelop the EGG into a more clinically relevant device. So my talk today is broken up into 5 main sections. I'm going to introduce modeling and how we developed some gastric models. Second, how we experimentally validated those models. Third, how we try to include biodiversity, which is a really important subject here. 4, how we defined completely new methodologies. And finally, how we have validated those in humans and animals at the very end. So, first of all, we developed 2 models, a torso model and a stomach model. The stomach model was based off a CT scan of a human subject, and then we're using a pre-existing model developed by Peng Ju. We were able to simulate gastric electroactivity moving down the stomach. We developed, gastric model. We then were able to place that stomach model inside the torso model and replicate the EGG fields through boundary element modeling to see what those surface potentials would look like under normal gastric electroactivity. So I've got a clip here showing two cases. You have already seen the normal case with just that propagation going down. And what I want to show to you is a dysrhythmic case, specifically gastric re-entry. And so you can see this little blip right there. We're going to have one mistimed activation, which is going to cause a complete destabilization of the entire stomach. So I'm just going to let that run. You can see how that one little blip is capable of completely destabilizing the entire stomach. So we can already see that that 3-cycle limit is gone, and we have a much higher increased rate, and we also have retrograde propagation as well as normal propagation. And so what we wanted to do with these models was look at the body surface recordings and see if we can actually identify differences between them. So for this, we investigated gastric re-entry, ectopic pacemakers, and finally conduction blocks. What I'm showing you here is a gastric re-entry. Ectopic pacemakers is simply another activation site on the stomach. And finally, conduction blocks are portions of the stomach that won't conduct any electrical propagation. So I'm now going to show you the exact same clip with normal and dysrhythmic on the body surface. Again, they're going to start off very similar. And then over time, they're going to become completely destabilized. And because we're going to run short on time today, I'm going to jump ahead. And we can see that they're completely destabilized. Obviously, we're not going to be able to take a full body scan of patients to get an image like this. And so what we wanted to do was we wanted to look at specific waveform morphologies and see if we could identify different gastric dysrhythmias. And very simply, these were the results. So we've got normal shown in orange on all the cases. And we can see that there is a morphological change on the body surface for all the cases. For gastric re-entry, we see in the blue the complete destabilization of the wavefront. And then in the ectopic pacemaker and the conduction block, we actually just see a change in that morphology. Because this was evident on multiple channels, these were the signatures that we were trying to look for when we went to human validation. But before we did that, we wanted to look at experimentally validating this in a controlled environment. So we're going to talk about experimental validation in the torso tank. So a torso tank is a torso shell. It was an old model that we put 190 recording electrodes, embedded 190 electrodes in the shell. And then we're able to reconstruct our gastric dipole using an artificial dipole source. This meant that we could validate our simulations without the presence of any background noise, which is one of the main problems with the EGG. We were also able to reliably reproduce the gastric dysrhythmias, which is another issue if we wanted to go straight into human subjects, because we wouldn't actually be able to identify what their conditions were, as we wouldn't have underlying basic understanding of their electrical activity. So for the torso tank development, like I said, we had 190 electrodes. We had this dipole, this artificial dipole here that you can see on the screen, which had 6 1D electrical sources, which was able to recreate a 3D dipole. This was then placed inside the torso tank at the location of the stomach, and we could reproduce those recordings. And so the question is how well did this compare to our simulations? How well did our simulations capture the experimental aspect of it? And so I'm going to let you guys be the judge. So I'm going to start the video, and this is a actual comparison of the simulated and the experimental results. And we can see that the simulated and the experimental match fairly closely. It's not perfect, I won't lie, but it will match very closely. So a video obviously doesn't tell the full story, and so what we did was we produced this figure here. So you've got all the different cases. You've got induction block, ectopic pacemaker, normal, and gastric reentry. And then on the bottom row, you can see the percentage difference between the experimental and the simulated cases. The findings were about a 2% difference between experimental and simulated results. And you can see on the bad channel why that kind of happens. The system was unable to capture those low dips, low dips in the simulations. And so this is, of course, an experimental setup, and we attributed this to actually experimental error rather than an error in the simulation. So that really begs the question, do these results represent a biodiverse range? If I go and put these electrodes on any of you, would you get the same recording? If we knew exactly that you had what the condition I said it would, if I put those electrodes in the same place, would we expect to see the same results? And that's a really important question, because if we went into clinical trials with this, we simply wouldn't know. We'd be looking for these signals that we have no actual understanding of how they differ between biodiversity. And so that brings us into the next question, biodiversity. How do we model a biodiverse population? So for this study, I investigated four different subjects based on human CT scans. We made we made the stomach models based on their CTs as well as their torsos, and we can see here just how different the biodiversity is. Obviously the torso shape is different, but the relative scale and positioning of that stomach is drastically different between each person. So simply placing electrodes on the body's surface may not be able to capture this biodiversity. And how does this, and the real question is, how does that actually affect the signal morphology? Is it going to be the same between patients, or is it going to be completely different? And that's what we set out to do with this biodiversity investigation. So I know there's a lot of text here. I will talk you through the images. So if we compare the gastric reentry to normal, we get this plot on the top left-hand corner. Second, we see the correlation coefficient. And then on the bottom row, we see the same for the ectopic pacemaker, the percentage difference, and the correlation coefficient. And what we wanted to do with the study was look at areas where we think that we could actually identify the differences between normal and gastric dysrhythmias. And so what we did was we built a system to look for these key areas across all the subjects of where those locations would be. And that's simply shown in the summary case in the red. So we've got this nice red blob right over the stomach surface. If we go back to what we did in the first simulations, we look at the signal morphology. Again, we can see vast changes to the signal morphology between reentry and normal the ectopic pacemaker case. What was very promising with this was there was a strong alignment between the ectopic pacemaker case and the reentry case, which says that there should be a position for each patient where we can actually identify gastric dysrhythmias on. But how does that red area in that summary align with other patients? Is that going to be the same across lots of patients? So across those four subjects, we see that that area varies greatly. It's not only not in the same position, the shape is different, and we can't identify that area simply by having a knowledge of what the stomach is, stomach position. It's actually isolated to every single patient. Every patient will have a different area where the signal morphology is actually different. And not only that, but if we look at the bottom plots between two of the different cases, we can see that the signal morphology, even on the normal cases, is drastically different. So now not only does this present a problem of we don't have the correct location, without an understanding of the actual baseline normal activity of that patient, a signal morphological approach doesn't really work. So we go back to that question of, do those results that we reported earlier represent biodiverse range? And put simply, no. We can't use those signal morphology, those characteristics, as a baseline for diagnosis for different gastric dysrhythmias. But it does raise a very valid point. The key point that we took away from this biodiversity investigation was that we really need to change the way that we're actually doing EGG. With the current EGG, we're using 2 to 5 electrodes, as we showed in the very start. If you're only recording from 2 to 5 electrodes in a standardized position, the chances of you capturing dysrhythmic behavior is extremely low. So what the field needs to do is they need to move away from this 2 to 5 electrode configuration and move to a high density array where we can guarantee that you're actually going to capture the signal of interest, or signal and area of interest, to increase that chance of capturing that dysrhythmic event. And this calls for a complete overhaul of the EGG device. And so what we're going to talk about now is the new methods to bring EGG into the modern age. So the first thing I'm going to talk about is increasing the spatial resolution of the EGG. So one method that's been used widely within the ECG field and EEG field is to use body surface Laplacians to increase the spatial resolution. And put really simply, what the body surface Laplacian is a weighted average comparing an electrode to those electrodes around it. What this can do is it can reduce the noise, it can amplify those signals and increase source localization, which means we should have a better understanding of where those signals are. On the downside, if you have a noisy signal, this will drastically increase the noise in your system. We also went back to the spectral analysis approach. So we originally decided to drop that because we wanted to be able to move away from that simple 3 cycles per minute. With the introduction of HIEGG, if we go back to it, we can actually start doing more sophisticated analysis with that spectral approach. And so on the far right-hand side, we can see in the blue a signal recording. And with the CWT analysis, we can actually get an overall breakdown of the entire spectral decomposition of the signal, which is shown on the far left-hand side, which is the integrated energy versus the pseudo frequency. With the CWT, though, we can also get a spectral breakdown of every single time step of the recording, which means that we can have instantaneous frequency decompositions, which will increase that resolution of the EGG once again. Once we have the CWT, we can determine the dominant frequency at every time step and use that to determine the phase of the signal. Because we're recording across multiple channels, a single breakdown of one channel is not going to be enough. Not for what we want to use it for. So we can see here on the far left-hand side, the CWT breakdown of a single channel. What we want to be able to do is actually look at the shared dominant frequency across all channels. So for us, that's about 64 channels. So the way that we've been doing that is using PCA to determine the shared dominant frequency, and then we can plot it on the far right-hand side, which is the dominant frequency of the entire recording array. I will come back to this. This is important later on. And so what does that actually look like on our body surface or on our simulations? So if we find the shared dominant frequency, we can decompose it, find the dominant frequency, and then find the wrapped phase of that signal. And that's shown on the left-hand side here in 7-second intervals. And so you can see that that phase is moving across. A wrapped phase doesn't really give us much information. And so using a 3D unwrapping algorithm, we can actually unwrap that and see the propagation of that phase across the body surface. We can then use that phase information to determine velocity and actually see how fast that wave is moving across the body surface. The reason why we've shown these three time points here is to show that even though the body surface Laplacian, shown on the right-hand side, is moving across the body surface, the velocity and the wrapped phase is consistent and stable. So what this means is that when we do EGG analysis with this kind of approach, we actually have stable results. It shouldn't be changing over time, and we should just see a nice stable result. Now, an unwrapped phase, a number between 6 and -6, doesn't really tell us much clinical information. If I was to go to a clinician with that, it wouldn't really tell us much. And so what we wanted to do is we wanted to convert that unwrapped phase into into a projected EGG activation map, or in terms of seconds. So using a simple equation and the known dominant frequency, we're able to convert that phase into the activation time, which is shown here between 0 and 40 seconds, which aligns with the stomach model as well. So using a combination of all of those techniques, what we wanted to do was we wanted to apply that to our 4 models that we had previously developed, and see if with these new techniques, they actually compensated for biodiversity. Could we get results out now with these new techniques that were actually stable across all these 4 subjects? So first of all, we've got the really easy cases. We've got the normal and the ectopic paces, which did not change the underlying frequency. And so you can't see it in these diagrams, but the blue line there shows the dominant frequency of the serosal activity and the EGG surface recordings. And we've got an exact match between the two. So the CWT method works really well at determining those the stable frequency results. But we also needed to make sure that it worked for the re-entry case. I am sorry, this is a bit of a complicated diagram. We did use body surface Laplacian, but we also investigated other methods as well. And this graph shows all of them. The green line on all 4, which represents the 4 different subjects, shows the dominant frequency of the serosal activity. The blue, yellow, and red show different techniques' ability to track that serosal activity. On the column on the left-hand side, we can see that the EGG dominant frequency was able to track the serosal frequency with a relative ease. And then on the right-hand side, we can see that it struggled to do so. The reason for this discrepancy, the reason why we weren't able to say, yes, EGG can track this instantaneously on the serosal surface, is because the actual serosal surface had multiple frequencies going at once. And so that's where we get to this plot here. The black line represents the average serosal frequency, whereas blue represents the range of the dominant frequency of the serosal activity. So if I just jump back, the reason why we have this slide is to show you that there is no one frequency. We want to be within that range, and we want to capture within that range. So if we jump back, the BSL was able to capture that range with relatively accurately. And so now we're going to look at the actual results. And again, because of time, I'm only going to show one rather than all 4. And so if we look at the normal case, on the top left-hand side here, we see the projected EGG propagation map. We can see that the phase is going from right to left, which aligns with the activation of the stomach at about 4.5 millimeters per second. When we look at the ectopic pacemaker case, the projected activation map is relatively similar, but we see an increase in velocity. When we go to the re-entry cases, we see a complete destabilization of that. We actually start seeing retrograde behavior. With retrograde behavior, the direction of the average angle is completely changed, and velocity now is up to 6 to 8 millimeters per second. These kinds of findings were seen across all 4 subjects, and show us that this kind of approach to analyzing body surface data was able to account for biodiversity and give us stable results across all the subjects. And so you'll have to excuse me while I jump through those different subjects. Quantitatively, we can also show the exact same thing, and I know this is a large data dump, but the key message is that we can see large differences on these reported metrics across all subjects. The dysrhythmias were associated with an increase in velocity and also a decrease in the R-squared value, or the stability index. And so what we're saying is that this method, in theory, can actually detect changes between the different diseases across multiple different subjects. And so that really, again, that begs the question, can we do this experimentally? Can we use these simulated results to get experimental data? And so for this, we did animal and human validation. The first was animal trials. We did dual surface recordings. So I'm not sure if you guys are familiar with the GI group's approach to record serosal data, but what it entails is opening up the chest cavity and placing recording electrodes such as this onto the actual stomach. We have 4 millimeter interelectrode distance and 192 electrodes, and we can actually take accurate recordings of the serosal activity so we know what's going on. Simultaneously, we placed electrodes on the animal torso to get the EGG data. That was done with 64 channels with 20 millimeter interelectrode spacing. On the far right-hand side there, you can actually see a recording of the serosal data in blue at the top and the EGG data on the bottom. And again, the frequency lines up. So to understand what the serosal activity was doing, we analyze the serosal data. The first thing we have to do is mark the slow wave data, which can be seen here. So we're looking for those spikes and those signals across all 192 channels and marking it with time. So here we see a full row of electrodes, and you can see that propagation is going down the stomach in a stable manner. To report those metrics, we're going to use 2 reported metrics. We're going to look at the slow wave frequency and also the grouped data. So the slow wave frequency was simply the time between sequential waves, and the group data was analyzed by grouping the activation maps, or grouping the activations into similar categories, as we can see here. So for group 1, it occurred at 68 out of the 79 points, and for group 2, it occurred in 11 out of the 79. Group 1 was normal behavior, with normal propagation going down the electrode array. And in group 2, if you look at the very bottom, you can actually see that there's a retrograde propagation coming back up the array. So for my PhD, we analysed 9 different things. I would be here all day if I wanted to talk to you about 9 things. So we're going to present 2 different cases. One which had one normal activity, but was unstable through time. So you can see that in the slow wave frequency, where it jumps around over time, but the actual activation map stayed the exact same through the entire recording period. In case 2, it is relatively stable over time. So the time between sequential waves is relatively the same, but then we start seeing this dysrhythmia occur at the very end, occurring at the exact same frequency that our normal behavior was. And so again, I've included this image here to try and show you, give you a full understanding of exactly what's going on. I will talk you through it because it is a little bit complicated. So in the top left-hand corner for case 1 and case 2, we've got our raw EGG recordings. Every step past that is a different filtering step that we did for my PhD, where we finally resulted in the bottom right-hand corner with the finalized results that we actually got. And so what we can actually see there is if we're looking at a single row indicated by the black box in that direction, we can see that there was stable activity moving from the right to the left on both the case 1 and case 2. So we can plot that with time for the serosal activity and the EGG recordings simultaneously. And what we're showing here is that as the blue dots, which represents the serosal activity moving across the electrode array, we have the exact same pattern, or a very similar pattern, occurring on the EGG moving across the body surface. So this indicates that our data is accurate, what we're recording is actually what we say it is. And also that we can actually tell the direction of that movement of that wave on the body's surface, as well as the, that it's stable across time. So the first thing is we wanted to compare the EGG data versus the serosal data in a spectral sense. And so on the left-hand side of both case 1 and case 2, we saw that you can see the serosal frequency, and on the right-hand side, and then on the red line, we see what the EGG is mapped. And so the EGG was able to very closely follow the changes to the serosal frequency. This is a big step forward, as this has not been previously been able to be done in the EGG, where they normally look at periods of 4 minutes. Here we can tell to nearly 5-second accuracy what the serosal frequency was doing. And then if we actually look at the propagation map, on the EGG, we see this normal propagation coming from the right-hand side moving across the left. And if we compare that with the actuation time of the serosal data, we get an identical result. So what this is really saying is, in this case here, we were able to capture this serosal frequency and match it with the EGG, and also capture the directionality and assign a velocity to that wavefront. So we're able to get a lot of information using this new EGG methodology. If we look at case 2, and the reason why we included case 2 was because of that dysrhythmic period at the very end of the recording, we can actually see the propagation map changing over time. So the stability index on the far right-hand side of the left plot, you can actually see when those groups occurred. So we started at group 1, which is at the top, moved to group 2, and moved to group 3. When we compare that to the serosal activity, we can actually see that this matches the serosal data. We started off with normal activity going across the body's surface, and then it became a little bit unstable, and finally we had retrograde behavior. So this method expands the clinical utility of the EGG, because not only can we tell the exact frequency, but we can also classify the directionality of that propagation within the normative range of EGG. And so then we went on to human trials as well, because we wanted to see if we could get this in human data. And so for this recording period, we had 20-minute pre-meal recording. Subjects were then asked to take a small meal, so water and a Cliff Bar, and then we did a 30-minute recording afterwards. And what we wanted to see was we wanted to see similar results to those pig trials. We wanted to see if we could get that same propagation directionality. And so this match, just a similar plot to what we showed in pig. Once again, we can see those waveforms moving across the body surface in the correct direction. So, in the correct direction. And then we can move on to the results, similar to what we just showed for the pig studies. So again, we had in group 1, we had normal activity moving across the body surface, and this represented about 90% of the total time. So this patient had normal propagation about 90% of the time. In about 10% of the time, we did see unusual behavior or retrograde behavior that was occurring within the normal frequency range. So again, this is a big step forward. The EGG has not been able to classify these directionalities in the normal range. If it's been in the normal range, it's simply been classified as normal. So what we're presenting here is a new methodology to actually compensate for, using HREGG to actually show that direction of the stomach and gain more clinical information off the stomach. We did this on 7 different subjects. And again, I'm sorry, I'm going to have to do a big data dump on you, but I'll explain what it all means. So the key summary is abnormal behavior increased after the meals, which is kind of, we hypothesize that this is actually a normal physiological response. So that abnormal behavior increased, and we attribute this to the mixing of the food in the stomach and stretching of the stomach. The frequency was unchanged, but there was an immediate dip. So if we look back here, immediately post-meal, which is this black line here, we see that dip, which has been associated with gastric distension. Is that what's happening in our data? Probably not, but we were stretching the stomach, so we can explain that immediate change. All patients, which were normal, which was 7 subjects, across all 7 subjects, had periods of abnormal behavior. And so, again, this goes back to that idea of if everyone was in the normal frequency range, but everyone had abnormal behavior, is this diagnostic? Can we use that to diagnose different conditions? Like I said, it was about a 9-to-1 ratio. And so what we need to do is now we need to expand this into people with functional disorders and actually see if that ratio is different. Can we see these same kind of patterns and behaviors in abnormal patients? And so that brings us into the summary of the future work. So EGG in its current format is purely a spectral-based approach. We can only get a normative range, so we can only say 3 cycles per minute is normal or the patient is abnormal. During my PhD, we tried to do a signal morphological-based approach, actually looking at those different morphologies, and it was shown that that was not possible due to biodiversity. We couldn't do that really use that kind of approach because of biodiversity in the population. But if we use a phase analysis-based approach with HREGG, so using up to 64 recording channels, we can then tell the directionality, velocity, and actually start diagnosing, patients that events that are actually happening within that normative range. So we can gain a lot more clinical information, which can then be passed on to doctors for diagnosis. So, like I said, if we combine all the findings, it may lead to increased clinical reporting and better diagnostic outcomes for patients. But there's a lot of work still to be done. We need to continue doing these dual surface recordings on more abnormal cases, so that we can get more data to understand what happens in abnormal cases. And then we need to also increase the population size of the normal cases in humans, and also include abnormal patients as well, so we can actually start seeing what those relationships look like and the the directionality starts looking like in those patients as well. And that should lead to increased clinical reporting for patients and clinicians. So I want to thank Dr. Peng Du and Professor Liu Cheng for looking after me for 4 years, and then also the Andrew Poland Doctoral Scholarship. And if there's any questions, I'm happy to answer them.
Does anyone have any questions?
I have 2 questions.
Go on.
One is a methods question.
Yep.
So you showed these plots of these wrapped and unwrapped phase plots of velocity.
Yep.
And you said that they were constant in time?
Sorry, I'm just jumping back to it.
That's one, yeah.
Yep. So the wrapped phase will change through time,
Yeah.
but the unwrapped should remain constant over time if the signal is unchanged.
What
If
about
the
velocity? Same thing?
velocity should be stable as well. We expect a little bit of change, but if the phase isn't changing, the velocity shouldn't be changing either.
So how does that velocity actually relate to the motion of this wave over the stomach?
So if theoretically they should be very similar, but it's sadly a non-linear problem. So, I mean, the way I like to think about it is, let's see if I can do this. Cool. Can you see the red dot?
Yeah.
We're projecting the serosal activity onto the body surface, which in this case is the board. If you're further away, the velocity will increase relative to the actual motion of that velocity of the serosal. So that's why you see this increase in velocity way over here, because the stomach's here. So that's why you see that it's a non-linear problem, so there shouldn't be a one-to-one relationship between the two.
So in pig number 1, we said it was non-constant in time. Does that mean it had different velocity fields?
Sorry, which slide?
Yeah, the forward one. So it's got its slope wave frequency is.
So the actual slow wave was relatively stable over time, but the interval between the slow waves were different.
Oh, okay.
Yeah. Does that make sense?
Yep. Okay. And then my second question is, you said sometimes you pick up abnormal behavior for a certain amount of time in your human studies.
Yep.
So does that mean the old methods that were just looking at 3 cycles per minute, were they sometimes classifying people as abnormal who were actually normal and just had a brief abnormal period?
So they wouldn't have actually detected that change at all.
Oh, okay. Sure.
They would have said that fell within the normal range, which is 3 cycles per minute plus or minus some variability, and therefore that would never have been assessed.
Okay.
Yeah, they never looked at the directionality of that actual analysis.
Yep. Thank you.
Hey, so you kind of just mentioned how you think about the serosal information as a projection on what you're measuring in the EGG.
Yep.
So how can you make sense of velocity and directional information in your human participants, because you don't, well, unless you've measured it, the actual orientation of the stomach
Will change, right?
Yeah. So
Yeah.
do you need to measure that before you can possibly make sense of velocity and directional information?
So this is a kind of up for debate. Like, I don't think velocity will be a good, in theory, metric for diagnosis, because depending on the orientation of that stomach, that velocity is going to change where you are, right? Also, because of where the stomach is, if I misplace the array, the velocity will change as well. But the actual propagation map, so the directionality of that this kind of directionality should be consistent across all patients, regardless of how the array is placed, regardless of your body structure, regardless of biodiversity, effectively.
Yeah.
So you're right, the velocity is probably not a good metric, but the the projected propagation map is.
Any other questions?
For the pig data, if you go back to that. So this before you go on forward.
Go on for it, so.
So just before it goes into group 2, there seems to be 2 dips in the
Yes.
sequence there.
Yep.
That actually, do you know if that actually was induced in the?
So this data is, I'd say, past this point here, the data starts to get a little bit funky. So it's been classified as normal,
Yeah.
but the actual slow wave, sorry, just going to jump back, does not look like this.
Okay.
So it's fallen to this trapeze. it's been classified, it's been able to classify it as normal waves, but it's kind of iffy if it is normal or not. But yeah, those two dips as well were a bit strange.
And as a pig, propagation frequency 4 rather than 3.
But
Pig's propagation frequency 4.
so it should be about
human.
3 as well. This one was just slightly elevated. Yeah.
One question about your biodiversity. You had 4 different subjects. Were the stomach distended or were they empty? Because that may have an influence in the size.
Yeah. So they all should have been empty. This is data I think recorded from 2005, or much before my time, and so I can't attest to the validity of that, but they were reported as empty. Yeah, but you're right, that would make a big difference, and those stomachs were so vastly different that we did consider that as well.
Any final questions? If not, let's thank the speaker.